Hi, my name is Kaylee Champion, and this is Cislunar Touchless Potential Sensing through Barriers. All right, so in a plasma environment, it's possible for two spacecraft to charge differently, particularly if one spacecraft were shadowed by the other. When this happens, when the spacecraft are docking and they get close enough together or they make contact, we can get an arc discharge between the two. Right, this can endanger the missions, it can fry important electronics, and so it's something we really want to avoid. This is actually a screenshot from a previous Applied Space Environments conference. This is a simulation from NASCAP where Orion is shadowing the lunar gateway during their docking operations. And we can see here that there's over a 9,000 volt difference between the two spacecraft. So this is obviously a danger of arc discharging in this specific configuration. So to avoid arc discharging during docking operations, we can actually use a technology that the ABS lab has been working on called touchless potential sensing. Where we actually are able to determine the potential of a nearby spacecraft before we make contact with it. So the method I'll be talking about today is passive potential sensing. So we'll be looking at the emissions that are naturally created from a target in space without using any sort of extra technology. So in this example, there's a negative target that is being irradiated with ambient electrons and solar UV rays, and a positive servicer that will be detecting its emissions. So that target will be emitting photoelectrons from the UV rays and secondary electrons from those ambient electron impacts. These electron emissions are emitted with very low energies, and so they are repelled from and accelerated to the target's potential, and then they would be attracted towards that positive servicer and again accelerated by the servicer's potential. So when they arrive at the servicer, their energy is equal to the servicer's potential minus the target potential. Servicer can then read this energy using something like an RPA or an electrostatic analyzer and can determine the difference in potentials. Now, touchless potential sensing has been under investigation for a little while now, but it's mostly been looked into in geosynchronous orbit. This was a good place to start because we've got highly energetic, very sparse plasma, and so there are a lot of complex spacecraft plasma interactions that we wouldn't expect to happen in geo. But right, cislunar space is a real big, exciting area right now. We've got Lunar Gateway. There's missions from all sorts of other countries that are being sent up, and even commercial companies are sending up their own landers and orbiters. And so if we wanted to take touchless potential sensing from geo to cislunar space, we're going to have to deal with a whole new range of plasma parameters and different spacecraft plasma interaction we haven't seen before. One of these is spacecraft wakes. So in a mesothermal plasma, the electrons are faster than the spacecraft, which are faster than the ions. So as a spacecraft is going through plasma, it'll move the ambient electrons and ions out of the way. Since the electrons are faster, they'll catch back up and continue impacting the spacecraft on all sides. But since the ions are slower, they're moved out of the way and they can't really catch back up quite as fast. And so we get this like low density negative region on one side of the spacecraft. It is important to note that in cislunar space, the wake always forms on the eclipse side of the spacecraft. This is because the plasma is coming from the flowing solar wind, which has bulk velocities of like 400 to 900 kilometers per second. And the spacecraft is only orbiting at less than a kilometer per second. But the wake could be an issue for touchless potential sensing because since it just has those electrons in the area, it has a negative potential field, which can then repel ambient electrons and change those electron emission trajectories or even just block them. In addition, we can get non-monotonic sheaths. So a typical monotonic sheath is shown in the top right here. So you've got your different particles coming in and the UV rays, and then those secondary electron and photoelectron emissions. And this thick sheath approximation would be kind of leaving the space. Or if the spacecraft is charged positively, some of them could be returning and being reabsorbed by the spacecraft surface. And the potential field would start at whatever the spacecraft surface potential is, and then decrease to zero as that distance increases. Under other conditions, so if the emitted electron to incoming electron ratio is high enough, and if the spacecraft size is comparable to the Debye length, and we'll talk about what comparable means in a few slides, we can get non-monotonic sheaths. So in this configuration, which is shown in the bottom right here, again, we've got the different particles and UV rays coming in, the secondary electrons and photoelectrons going out, but now we have a thin sheath, and so those electron emissions are settling near the spacecraft surface. And so since we've got an abundance of electrons near the spacecraft surface, the potential field there is more negative. So as you can see in the plot, the potential field will start at whatever the spacecraft surface is, go somewhere more negative, and then start to trend towards zero. And what this does is whenever any sort of future electrons or UV rays come in and create those secondaries and photoelectrons, they're going to escape from the surface, see that kind of negative wall, and then be repelled right back into the spacecraft surface. And so this can really just suppress lots of electron emissions. So if it were to happen around the target, those emissions would be suppressed. We couldn't sense them at a servicer, and we couldn't do our touchless potential sensing. So first we want to determine the conditions under which non-monotonic sheaths in wake would create barriers that electron emissions can't get through. If these barriers do in fact prevent touchless potential sensing, and what kind of ideal conditions we could create to overcome these barriers while doing sensing. All right, this first goal is investigated using simulations of a single spacecraft, and the next two would be investigated using both the servicer and target in the simulation. The simulations are done in space. So the particle and cell electrons and ions were modeled in space. We have a 0-volt boundary on the outsides. The surface resolution on the spacecraft is half the photoelectron to length. And then on the external boundary, it's half to a quarter of the electron to length. And then that boundary was just set far enough away that the potential field could trend to zero naturally before it hit that 0-volt Dirichlet boundary. This was also done in two environments. So there's one sunlit environment and one eclipse environment, both in the solar wind. In the sunlit environment, the photoelectrons would be creating that non-monotonic sheath. The secondary electron yield was set low enough that it wouldn't be high enough to create the non-monotonic sheaths or those barriers. So we'll just get that. So we'll just get barriers from photoelectrons and from the wake. And then for the eclipse spacecraft, right, there are no photoelectron yields, and the max secondary electron yield is increased, so that we might expect non-monotonic sheaths from the secondary electrons and then also barriers from the wakes. All right, so let's get into the single spacecraft results first. So first simulations were done just with a floating spacecraft. Right, can charge to whatever it's going to charge to, and we varied the width. And as you can see, right, we've got plots in the sunlit and in the eclipse environment. In these plots, the negative x position would be the wake side of the spacecraft, and the positive x position would be the ram side of the spacecraft. So if we look at the sunlight results first, you can see that as the spacecraft gets larger, the barrier gets larger and it starts to charge more negatively. We can kind of start to see that barrier formation when the spacecraft is like 0.6 to 0.8 times the Debye length. Then for the eclipse spacecraft, again, as it gets bigger, barriers get bigger, electrons are suppressed, and the spacecraft charges more negatively. We start to see those barriers form at a little bit smaller of spacecraft width to Debye length ratios. This starts happening more at like 0.2 to 0.3. Right, we can start to get barriers when the spacecraft is less than a third or less than half of the Debye length. These are just some photos to complement those plots. So on the top, we've got the potential field. On the bottom is the photoelectron density. And then the left plots would be the smaller spacecraft. So no barrier, right? We've got a bigger one. So those barriers returning. But you can see in the top left that photoelectron barrier, sorry, that potential field, right, trends monotonically towards zero away from the spacecraft. Whereas on the right, we've got that negative region where that wake is, and then a negative region where those photoelectrons have settled. Then with the photoelectron densities on the bottom left, we've got the photoelectron sheath that fully surrounds the spacecraft. Whereas on the right, there's a big negative region on the wake side of the spacecraft where the photoelectrons just can't enter. So if we were trying to detect potential with a servicer in that area, it'd probably be pretty hard. Same thing again, but now we're looking at the eclipse spacecraft. So we would have barriers with the secondary electrons. Again, top left, monotonic sheath. On the right, we've got that negative region in the wake, and then that kind of green cloud surrounding it is actually the non-monotonic sheath from the secondary electrons. Again, bottom left, secondary electron sheath fully surrounding the spacecraft. And then bottom right, that sheath is kind of pulled in on the wake side, so the secondary electrons can't reach quite as far away from the spacecraft. All right, so now after doing the floating potential results, it kind of seems to indicate that there was also a relationship with the spacecraft potential. So I did runs with constant potential spacecrafts of varying widths. And so these plots have the barrier size on the y-axis and then the spacecraft potential on the x-axis. And what we can see is that once the spacecraft reaches like 10 volts positive, those barriers just disappear. And that's really just because the emitted electrons are being attracted back and absorbed right into the spacecraft surface. But we also see that for higher spacecraft, we get larger barriers, right? That's also what we saw with the floating spacecraft results, so that's expected. But those barriers are able to persist quite a bit more for negative spacecraft. You can especially see this in the sunlit spacecraft results. But then regardless, in any of these simulations, with the 0.2, with over divide length spacecraft, we really don't get any kind of barrier size results. So at this point, we're kind of safe. All right, passive potential sensing results. So established that there's 4 different kind of environments. There's sunlit with and without a barrier, and there's eclipse with and without a barrier. Within each environment, there are 2 different servicer potentials that I was interested in testing. One would be a 50-volt servicer. So if we had some sort of spacecraft potential control, this would just keep it more positive than the target. But with a 300-volt servicer, the idea would be to accelerate the ambient electrons so that these accelerated electrons might then impact the target and create more secondary electron emissions. So this would ideally make it easier to sense. And then within all of those, there's 3 relative positions that were tested. So there's a servicer in the target's wake, target in the servicer's wake, and then both wakes parallel. So this is a total of 24 runs. All of these were done with 1 spacecraft width separation, and then the servicer and target widths are just set equal. I'll just be talking about the sunlit spacecraft results for the sake of time, and because the eclipse spacecraft results conclusions are really the exact same. But just to run through this graph real quick, table real quick. So the servicer's potential is shown on the left. Then we've got, right, the spacecraft widths, which is the meters over divide length. Then the position of the spacecrafts, whatever the target floating potential ended up at, the fraction of emitted electrons that were recollected by the target, and then finally the detected electron current density. So this is what would be used for Tesla's potential sensing. We can see in this graph, in this plot, we can see in this table that the target in the servicer's wake is the worst for sensing. Right, we have the minimum detected electron current in this configuration. This is because with the target in the servicer's wake, right, it's getting impacted by very little ions. And so since it's getting impacted by less positive particles and really only negative particles, it charges very negative. And then it actually ends up repelling nearly all of the ambient electrons. So since it's being hit by very little ambient electrons, it's emitting very little secondaries, and it's shadowed, so it's emitting no photoelectrons. So you can see that in this figure here. Right on the right, we've got the log of the ion density. You can see that target is just fully enveloped by the servicer's wake. And then on the left, you've got the electron density. So there are really no electrons surrounding that negative target. Next, we see again that more current is recollected for the larger spacecraft, right, and less is sensed for the larger spacecraft. This makes sense again, right? This is when we would expect barriers to form. But we don't see it just killing the sensing, right? We're still able to detect something. It's not just a massive uptake in the fraction of electrons that are recollected. So this bodes well for sensing. And part of this is because the positive servicer is able to kind of break through the barriers and pull in those electron emissions. And I'll show some figures for that in a couple slides. And then last, the 50-volt servicer actually ended up being better for sensing, which was surprising. One, this is because, right, a less positive spacecraft will have a smaller wake. So we don't get that such a significant wake effect when the target is in the servicer's wake. And so we're actually able to detect some sort of electron emissions. And then in the other configurations, because the servicer is causing the target to have fewer secondary electron emissions, the target doesn't charge quite as positive. And because the target is not quite as positive, the electron emissions are more susceptible to being pulled in by that servicer. So previous research has showed that the more neutral a target is and the more positive a servicer is, the easier it is for us to do touchless potential sensing. So we're basically just approaching those conditions with the 50-volt servicer. So right here are some figures to kind of support that. So on the top, we've got the smaller spacecraft, so right, no barrier formations. On the left, 300-volt servicer, and then on the right, we've got the 50-volt servicer. Right in these figures, the black box is the target on the left, and then the right is the servicer. And this is the configuration for the servicer and the target's wake. But as you can see, photoelectrons are kind of surrounding both spacecraft in all of these conditions. So that positive surfacer is able to kind of break through any barriers that might be there and actually pull the photoelectrons at least away from the target. But the 50-volt surfacer is a little bit more efficient at pulling those photoelectrons away from the target and then into its own face. So you can really see that in these top two pictures. So with the 300-volt surfacer, those photoelectrons are emitted. They're pulled towards the surfacer, but they kind of look like they almost orbit the two spacecraft. Whereas on the right, with the 50-volt surfacer, those photoelectrons are pulled away and their path is much more direct. You can kind of see that like triangle right into the surfacer's surface that's facing the target. Um, yeah, so just interesting conclusion that 50 volts is better than 300. And then finally, we just wanted to make sure that the electrons that were detected could actually be differentiated from the ambient electron environment. So these are energy bins that would be measured by, right, like an RPA or an ESA. But basically, it's the current density that would be found between two specified energies. And so what we can see is on the left, we have the RPA measurement to a 50-volt smaller servicer with its wings parallel to the target. So this is a more ideal scenario, right? And those secondary electron emissions would be expected. Secondary electron and photoelectron emissions would be expected in that first current bin. And we do see a large uptick there, so we could definitely differentiate from that ambient environment. On the right, these are the measurements to a 50-volt, right, much larger servicer with the target in the servicer's wake. So this is a less ideal position. And that vertical line shows the energy band where we would expect those secondary electrons to come in at. Again, we see a large uptick there. Right, it's not quite as sufficient as quite as large as the ideal scenario, but this still should be differentiable from the ambient electron environment. So we can do sensing both with the ideal setup and with the less ideal setup. Right, so just to recap, right, barriers can form when the spacecraft width is less than half the Debye length, and they persist a little bit better for longer, for more massive spacecraft and more negative spacecraft. 50-volt servicer seems to be better for touchless potential sensing. It's really best for the target to be outside of the servicer's wake, both for charging and for sensing purposes. But we can, in either way, use those passively emitted electrons to determine the target's potential. Thank you. Are there any questions?